Alrighty, let's have a look at another version of our characteristics problem. This is very similar to the one in the other video, so much so that I'm not writing this out again. It's exactly the same setup. We've got hyperbolic conservation law. We've got the same velocity of objects as we had. So this is the velocity of our stuff. This is the flow of our stuff from our usual relation Q equals rho U. Now, we obviously want to substitute out Qx and replace it by something to do with rho, so we've got a PDE for rho. Right, so we differentiate with the chain rule and we plug in and we find old mate Berger's equation. It's a first order Berger's equation. It's a first order quasi-linear PDE, so it's amenable to characteristics. We parameterize space in terms of time, these characteristic curves, x as a function of t, and we use our chain rule to work out the total derivative of rho with respect to t. Now, by comparing this chain rule result to our PDE, we observe that we've got two ODEs. If dx dt equals rho, this thing here, then the total derivative of rho with respect to t is 0. So this defines our characteristics. This defines our density on the characteristics. Now, this says that density is constant on those characteristics. All right, now, I haven't actually specified an initial condition yet, but I know that for all times, that initial condition is just going to be shifted along or sort of pushed along our characteristic curves. The initial condition I'm going to specify is very similar to the one that we saw in our shock video. However, it's changed direction. Now what we have is at the 0 jump, we go up in density. Boing! Like so. Oops, they should be blue. That looks really bad. Okay, so at 0, we have this jump in our density, right? And it's 1 there, and it's 0 on the left. Okay, so now what we can do is, because we're on the characteristics, right, we can find our we can substitute this rho with this thing and find our characteristics. Okay. All right. What that says is that we've got vertical lines on the left of the origin, where x is just some constant value for all values of time. And on the right-hand side, we've got straight lines of gradient 1. So let's sketch that in. X, t. If x is less than 0, we just evolve the initial location of x in time, independently of time. So we just stay at x naught for all times. If we're here, right, we got some starting point here. We're going to evolve t equals x minus x naught, right? So you can see that that's a line of slope 1. What's interesting is that as x naught gets closer and closer to the origin on both sides, right? So I'm going to draw a characteristic just to the left and a characteristic just to the right. That's the best we can do to fill in our domain. Oops, that's a bit sloppy. Now you'll notice I'm drawing in lots of characteristics, but I can't get any information in here. This is lost, right? I've got nothing in there. There's no characteristics that cover that region of space. So if you like, this characteristic here, just to the left, this characteristic here, just to the right, they're somewhat important. They're somehow critical boundaries on where we can find solutions when we can't. So let's just figure out what this line is. That's the line t equals x. I'm just, I guess, just to the left or just to the right of the origin, but you know, like that's 0. So it is right. It is t equals x. Now on the characteristics, I know what my solution is. So on this line and over here, I know what my solution is. To the left of this, to the right of this line, sorry, so this region in here, to the right of t equals x, that is x greater than t, greater than or equal to t, say, I know that my density must be 1, right? Because that's what it was originally. So somehow my density has moved out here, right? And is propagating along. Because we know that our density is constant on these characteristics. Right, so that's the first bit of information that we've got. We've partially reconstructed our solution. We got 2 more bits to do. To the left here, if x less than 0, right, which is everything to the left of this yellow vertical line, we know what our density is. Our density must be 0. It's here. X less than 0, rho equals 0, right? That's just from knowing what happens on these characteristics. That's all we've got so far, right? Which means there's like this evolving gap in our solution. Let's try and sketch out our solutions so far. So this is now rho x, and I'm going to draw in a couple of times. So at time 0, we've got this. At time, let's say it's 1, x greater than 1, I know my density is 1 as well. And I know that down here, x less than 0, my density's 0. But I got no idea what's going on in this region here. Now, it's tempting to fill that in with some sort of straight line regularization. We think of a low density expanding to this high density. right, along our fan. Now these, they don't have to be expansion, like they can shrink as well, they can drop down if you've got the reverse of this situation, right? If you've got a fan-like characteristic, you've got something called an expansion wave solution. And what you're trying to do is you're trying to fill in that, that gap between where your characteristics stop on one side and where they start up again on the other. So how we regularize this problem is we just assume that at that jump, at that initial jump, there's all the densities, I guess, right? So what you want to do, let's draw out our characteristics again. Right, just these important ones. What you want to do is you want to fill this in, right? Each one of these taking a different slope value between 0 or between infinity and 1, right? Now, if you actually go and look at your characteristic equation, right? Recall the total derivative, dx dt equals rho naught, right? Because it's the initial density. Imagine if instead of at that jump, you don't have just sort of 2 points of information, but you've got all the values of density in between, right? You're going to get x equal rho naught t plus x naught. X naught is 0, right? All of these characteristics are thought to originate from the same point, the origin in this case, right? It's the intersection where your fans occur. Doesn't have to occur at 0, just so happens it occurs at 0 in this example. So you got x equals rho naught t. Now you can write that as rho, or actually rho naught equals x over t, right? So that's imagining that the density can take all the values possible within this fan. And that's it. You're supplementing your initial condition here. You're actually sticking more information into the problem. You didn't have this to begin with, but you were dissatisfied with the solution. So by sticking all of this in, you actually have this solution in here. You have this extra bit that rho equals x on t. It doesn't, in this result is sort of general, right? In as much as you let rho fill in all the values between its limits, but you don't necessarily have to get this simple an expression for your overall density. You could have an x naught in there. You could have some sort of number in here as well, right? So just be aware of that as you're thinking these problems through. But yeah, this is what, in this case, we end up with. So in the fan, we've got, we discover, I guess, we have rho equals x on t. So let's now write out our complete solution. Rho equals 0, x less than 0. Rho equals x on t, x greater than 0, less than t, 1, x greater than t. So that's our expansion wave solution. So X row initial condition time 1. What's the new color? Time 2, I guess. Like so. All right, so that's the fan and expansion waves.